Look at the calculator app on your phone. It's light, instant, and fits in your pocket. This 400-year-old book of mathematical tables performs the same core function. It's a physical software designed to provide instant answers to difficult questions. The book relies on mathematical constants. You can think of a constant like a saved setting. It is a specific number, found in nature, that stays the same no matter where or when you measure it. You've likely used pi to measure circles, but there is another constant called e, which is roughly 2.718. This sweeping curve shows what e represents, the specific rate at which things in nature grow and expand. Before digital screens, these printed numbers gave people a reliable way to calculate the behavior of the physical world. For centuries, if you wanted to measure something you couldn't reach, like the height of a mountain, or your ship's distance from a star, you had to use right triangles. This created a massive bottleneck for sailors. Calculating a ship's position meant multiplying long strings of decimal numbers by hand. A single arithmetic error in the middle of the night could lead a navigator to believe they were safe in open water when they were actually seconds away from hitting a hidden reef. To navigate safely across the globe, people needed a way to make these life-or-death calculations faster and more reliable. The book provides the values for 3 core tools: sine, cosine, and tangent. These measurements tell you the exact relationship between the sides of a triangle based on its angle. Each of these has a helper version looking from the opposite direction, known as cosecant or secant. They are simply the core measurements flipped upside down. Navigators also used specific tools for specialized tasks, such as versine and coversine. These were essential for the precision required when using a sextant to find a ship's location by the stars. Take versine, for example. If you visualize a circle, the cosine tells you the horizontal distance. The versine is simply the leftover space between that distance and the edge of the circle. It allowed sailors to calculate their curves without starting from scratch. These weren't just abstract terms. They were the measurements a sailor used to survive the journey and find their way home. Even with those tools, the math was still slow. To speed things up, the book used a logic trick called logarithms. You can think of a logarithm as a shortcut that reduces the complexity of a problem. The shortcut is powerful because it transforms difficult multiplication into simple addition. Instead of multiplying 2 massive numbers, you look up their logs in the book and just add them together. The book tracks these shortcuts in 2 ways. Common logarithms work with the number 10, which is how we usually count. Natural logarithms work with that constant e, matching how things change in the real world. These tables acted as a translator. They turned basic counting into the complex math needed to understand natural growth and motion. By simplifying the work, logarithms provided the processing power that allowed engineers and explorers to solve problems in minutes that used to take hours. Using the book was a simple loop. Find your angle, find the right column, and read the number. But what if you needed an angle that was halfway between the numbers printed on the page? You would use interpolation. It's like using a ruler to estimate a middle point between 2 inch marks. You look at the gap between the printed numbers and calculate where your specific angle would sit. This estimation trick allowed a single book to provide the precision needed for almost any calculation, even the ones it didn't explicitly print. If you look at the columns for small angles, you'll see values that start with a 9, like 9.69. This looks strange because the actual math is quite different. Small numbers actually have negative logarithms. However, adding and subtracting negative signs by hand is confusing and leads to mistakes. The book uses a simple fix. It adds 10 to those negative numbers to hide the minus signs. This creates a clean, positive value on the page that is much easier to work with. This was early user interface design. The creators hid the messy math to ensure the person using it could work quickly and without errors. While we have digital calculators today, these old methods are still the foundation for how we understand the world. By learning to use constants, triangles, and logarithms, you are learning a specific sequence of logic. Combining these ideas leads to calculus, the branch of math we use to model how things move and change over time, from the path of a planet to the growth of a population. These paper tables provided the first practical way to manage those calculations, giving people the tools needed to finally start measuring the motion of the world around them.